What's up, illustrators? Okay, so I want to talk about in this video a cool innovation that I invented. So if you look at this, figure that I'm preparing, right? Like I'm showing PCR results. I'm showing essentially a positive control, and then if or if not, this band was detected corresponding to this HG3 PCR. Okay. And for each of these samples, this figure is not finished yet. I'm working on it. But I wanted to show you this innovation. So for each of these lanes, there is a separate DNA extraction. So one was a separate DNA extraction. Two was a separate DNA extraction. On and on and on and on to n. Okay. And for each DNA extraction, there's variable amounts of yields of DNA. Like not all DNA extractions are exactly the same. Not all samples are the same. And you get a great variety and variation in the quality of the DNA yield. Okay. So traditionally what people will do to mark their lanes is, like I showed in the last video, they'll make something like a lane marker and they'll pop it over top the gel, and then you know where each of the lanes corresponds to, because that just helps you understand visually when you're looking at blank spaces, like where the samples are. Okay, that's traditionally how people do it. So I feel like each of these DNA extractions, because it's an independent extraction, one of the key controls is how good is that DNA for each of these samples, because somebody might say, well, in this sample, if the DNA was very, very poor, that might be why you got a negative reaction. It might not be that that particular sample was actually negative. It might be that the DNA extraction was actually really bad. So one of the controls for quality of DNA extraction is the yield of DNA. And you can calculate the yield of DNA by a nanodrop. So you just take a drop of your DNA, run it on a nanodrop, and you'll get a number that corresponds to nanograms per microliter of DNA. So one of the things that we thought would be valuable would be to show as a control the quality of the DNA extraction for each of these samples. So we thought, well, we could put a graph of nanograms per microliter above the lanes to quickly show the quality of each DNA extraction. And then in this case, you might particularly say, well, look at the quality of the DNA extraction. Look at the yield here. It's either 0 or it's maybe like 1 or 0.0 something. It's very, very poor DNA extraction. So that might be why this one was negative. So it's actually like really useful information, and it serves a dual purpose in a sense that now I don't need a lane marker. I don't need these lane markers anymore, because I'm showing you the dots which correspond to the graphical nanodrop data above each lane. So I thought this was a really cool innovation. I really like the way that this turned out, and I want to show you how I make this. Okay, so for each of these lanes, each of these samples, we have corresponding numbers in that correspond to the nanograms per microliter yield of the nanodrop. Okay, so I just write these down. So this would be sample 1, sample 2, sample 3, sample 4, sample 5, sample 6, sample 7, 8, and 9, etc., etc. Okay, so one of the things that you can do is you make a graph, and this is an ugly graph, a shitty graph. Okay, but you make the graph in Excel. So you just do this by, let me quick show you how to do this. You can make this graph by usually I'll include just like a random 9 is actually not a sample. I'll just include a 50 to sort of like standardize the axes. Okay, so let's insert a scatter plot. Very, very easy, quick. And now what I'm going to do is I'm going to shrink the scatter plot so that the y-axes are 50, the ticks are 50 and 100. Okay, so now this is a graph. This is a graph proportioned perfectly where the tick marks are 50 and 100 nanograms per microliter. Okay, now I'm going to copy that. I'm going to put that into Photoshop. Okay, so you get this graph that looks like this. And now what I can do is I have made this, constructed this y-axis bar. Okay, this y-axis bar. And I can resize proportionately this graph. And if I can't see the bar, I can make the opacity lower. Okay, and I can perfectly resize this so that the points on the tick marks on the axis, hang on a sec, it's going to take me a second. so that the points, the tick marks on the graph correspond to the y-axis marks that I made, okay? And then what I can do is I can take this and I can make it so that each lane, each dot corresponds to the lane. And if you have your lane marker scale bar here, that can help you out. So what I want is I want roughly each dot corresponding to each lane. Make sense? Okay. Now I have create a new layer. Okay, I have my brush and I'm setting it to, I have a standardized pixel dot, 36 pixels, okay, with black. And now what I'm going to do is I'm going to make a dot exactly where that point is. Now, one of the criticisms of this method might be that each of these dots, because I'm manually making it, could be off by a tiny fraction, right? The answer to that criticism is, what's the purpose of this? Is the purpose of this to get a precise number between 50 and 0 that corresponds to the exact decimal point corresponding to the exact nanograms per microliter? No, that's not the purpose of this. The purpose of this part of the figure is twofold. One, to use the dot to mark the lanes. Two, to give you a rough estimate of the quality of the DNA extraction. So what we'll probably do with this is we'll probably make a supplemental table that holds all the precise, accurate values that we put into like an Excel file. That'll be a supplemental figure, but something like this gives you a real good sort of like quick estimation of, was the DNA control good? Was it a good yield of DNA? And was there a positive band or not? So I feel like this is a really interesting, unique innovation. I've never seen it before. I invented it, and I feel like it's worth sharing because I think this could be really useful as a way to show controls and gels all in the same figure space.